Hi there. In this video, I want to talk about Electra pre-training text encoder as discriminators rather than generators. This paper is published in 23 March 2020 and bring a new way, very similar to GAN for training a language model. I will go through the paper, then we will implement the Electra, which can be used for training any language models that can achieve better for performance than training a language model with traditional way by masking tokens. As an alternative, we propose a more sample efficient pre-training task called replace token detection. Instead of masking the input, our approach corrupts it by replacing some token with plausible alternative sample from a small generator network. Then, instead of training a model that predicts the original identities of the corrupted tokens, we train a discriminative model that predicts whether each token in the corrupted input was replaced by the generator sample or not. So basically, if I want to explain what's going on here is we have language model that we pass some tokens to it, like the chef cooked the meal. And for training a language model, we mask some of the tokens, and usually we mask them randomly, like when we have Wikipedia pages of data. So we grab sentences, corpuses, and mask some of the tokens, and we let the language model to predict what was the correct word or correct tokens for that specific corpus. So the paper said, instead of using that type of learning, it's good to have a method like GAN. It is not trained based on adversarial loss. It is trained based on maximum likelihood, but it can be trained in a very similar way that GAN is trained, that we have a generator and we have a discriminator. And the generator, as here is shown, it is typically a small mask language modeling. We have tokens and we predict mask token by the generator, and the discriminator is just saying that which token is replaced. So when we have a sequence of tokens, we can mask each of them randomly. For example, for the first time, we mask Z here, and the output, the generated sequence is predicting something right. So discriminators said that this is coming from the original. But if the generator is predicting something different than the original text, the discriminator should say that this is something not equal to the original and this is replaced. So in that way, we can pick random positions. Each time I can put mask on different tokens, and based on the prediction that generator has, we train the discriminator to understand, to learn which token is replaced and generated by the generator is not the original text. That is like an unsupervised learning for mask language models. So let's back to the paper. They said this approach of training is very similar to the GAN, but it is not adversarial, and they are using the maximum likelihood due to difficulty of applying GAN to the text. Also, it cannot be used by the GAN approach based on adversarial because the backpropagation cannot be applied on those sampling. They said, given an input X, so we have these tokens, first select a random set of position, integer between 1 and n, the number of tokens. So we select random positions to mask them. And the tokens in the selected position are replaced with a mask token. And we denote this is a X max and replace them. So we say replace X with this mask for a specific position. The generator then learn to predict the original identities of the mask out tokens, and the discriminator is trained to distinguish tokens in the data from the token that have been replaced by the generator samples. So you can see that the loss formulation for the language model for the generator is similar as the mask language model, and the loss for the discrimination is like a discriminator network in the GAN. And finally, the total loss of the system when we want to train that is based on the mask language modeling loss plus a lambda and the discriminator loss. They said, as I said, we don't backpropagate the discriminator loss through the generator. We can't because of the sampling step that we randomly generate some of the mask tokens. And they have in the appendix a way that using the reinforcement learning, they could train it, but they showed that the trained system by reinforcement learning is not getting good accuracy as when we train it with this loss. After pre-training, we throw the generator and fine-tune discriminator on downstream task. So instead of training the generator, training the mask language model, we train a discriminator and we use that discriminator as the final model. We don't need a generator anymore. The discriminator actually is creating some hidden representation, and those hidden representation then is converted to the binary for maximum likelihood loss, which is shown here. So we have the hidden representation of discriminator, and they are just some linear Lagrange sigmoid to get the output that it is original or this is replaced. So very simple, very interesting. And for training, they also said, we train only generator for n step and initialize the weight of the discriminator with the weight of the generator, then train the discriminator with loss of the discriminator for n steps, keeping the generator weights frozen. And they do repeat it until get the termination criteria. So they said that the weight initialization in this procedure require having same size for the generator and discriminator. We found out that without weight initialization, the discriminator would sometimes fail to learn all beyond majority classes, perhaps because of the generator started so far ahead of the discriminator. This is also an important issue we needed for the implementation. So when we compare this method with others like the Roberta for different tasks, like for question answering SQAD, like here, or like when it's applied on the glue test result, the model trained based on the Electra is gaining better accuracy. So you can see in different approaches, like in SQAD, they are getting 88%, like while the Roberta is getting 86. So yeah, that's it. Now it's time to have a simple implementation of the Electra that can get any language model and train a better language modeling based on the discriminator for us. Okay, let's start coding. I searched on Google and found different repositories and implementation, but I found LucidTrain repositories cleaner and more understandable. That's why I picked it. And I didn't change it that much, a couple lines. And I have a unit test. Everything is copied. It's not written by me, but I will try to go through each line and show you how is it working. So we have two language model. One is the generator and one is the discriminator. And the generator size should be usually bigger than the, smaller than the discriminator. So that's why here depth is 1 and depth is 2. Instead of these reformer language modeling, we can use any other language model like the BERT or Roberta or stuff like that. So this is because it was in the repository I'm using those. And the important thing is that the token embedding and positional embedding for the discriminator and generator should be same. And then we can define a mock data. We are supposing that we have a vocabulary list containing 20,000 words. And we are passing the data with batch size 1 and with 1,024 words. We are passing that data to a trainer, which is Electra. And Electra, I will show you that it get the generator discriminator. Total number of tokens, as I said, is 20,000. And discriminator dimension is 512. From the paper, you remember that discriminator should be based on the binary cross entropy. But now we have language modeling, and that's why we have a discrimination layer, which means that we say to the Electra that the hidden representation are in those layers. So get those hidden representation and add a linear layer after it. So there are some tokens like CLS, like separators, SEP, and also the padding, PAD, that we don't want to mask them. Yeah, that's why we pass them to mask ignore token IDs and pad token IDs. Let's run this unit test and show you how it is. So we will get data between 0 and in size of 1024. Each item has a value between 0 and 20,000. And we go to the Electra. The Electra forward function is here. So the first thing is replace probability. I can explain it this way. So we have input in size 1024. Replace probability is a Boolean vector in size of the inputs, but each item can be true or false. I think that replace probability is used here just for increasing the sparsity. I will explain it later. But maybe removing that doesn't harm the code. I don't know, I haven't tried it. So we have mask with tokens. So we get the inputs and we said, give me a mask in size of the inputs that in place we have special tokens like CLS, padding, and separator, and stuff like that. Set the value true. In other places, set the value false. So we will get the mask for special tokens. And we call them no mask. So the reverse of the no mask is the mask that we want to use it for masking words. So we have a get mask subset with probability. So this function is written somehow that we get those masks. We pass the mask that we want to apply a mask on the words. And we get the probability. We call them masking probability. And what it returns is a mask that is somehow equally distributed through the length of the text. And also it is sparse because the language model needs to know some of the text to get the information and tokens from them. We can apply it in any other way that you think. So we want to just create some true and false value, but the true value should be sparse through a 1024 false vector length. And also it's better to be equally distributed. So we get the mask. The next thing is we want to get the indices of the mask. We have this vector, we want to say which indices of this vector has true. So we will keep it. So the next thing is we want to get the generator labels. And why we need that? Because you remember that we have generator, we pass the inputs, we get the outputs, and we need to have a loss for it. And the loss is the cross entropy loss that we have it here. And we need the generator label and the logits coming from the generator. Let's first explain this part. So we know that we have the mask. So that mask can be used for masking the inputs. But as I said, there is a replace probability, which is a vector in size of the input that is multiplied to the mask that we have calculated. As I said, I think it is not essential, but maybe it's adding a layer of sparsity. This mask input is the input that some of the tokens that is not a special token are masked. And we pass them to the generator and we get the logit and we get the loss of the language model. But one thing is we don't want to calculate the loss of the language model on the some special tokens. That's why we change all of the special token IDs to pad token ID. And when we are calculating the loss, we say ignore those tokens. For those words and for those indices that we apply the mask, we want to get those sample. If you remember the block diagram, you will see that for those tokens, you want to add a little noise or change them and pass them to the discriminator. Now the discriminator needs to say, is it original or it is replaced? So we call them sample logits, the mask indices of the logits, and we apply a little noise to them. This Gumpel noise is a uniform distribution passing through two logarithmic functions and has a temperature. So it's just, it can be any other noises that we can think of, but it shouldn't be that much drastic change. It should be a small little noise, change the token a little. So the discriminator input is same as the inputs, but for those indices that they are masked, we replace them with the sampled. We replace them with the noisy ones. We need the labels for discriminators. And maybe after applying the noise, the token doesn't change. So for calculating that, we are just saying, is the input is equal to the discriminator input? And if it is not equal for those indices, we are setting true. Again, we don't want to calculate the binary cross entropy loss for the padded tokens, for pad tokens IDs. And we pass the discriminator input to the discriminator function, get the logits, and we calculate the binary cross entropy loss. So one thing that is remained is here that we have argmax for the logits of the generator. And also for the discriminator, we have, you remember that we have sign of the logits in the formulation in the paper. So we have the discriminator prediction, generator prediction, accuracy of the discriminator and generator. And also we have this formula, which is the main formula of the paper. The generator weight in the paper was 1. So we have 1 in language modeling loss plus the lambda or discriminator weight multiplied by the discriminator loss. So we can define any other weight here, and it will return us the result containing these variables. So after getting result, we can do the backward. One thing that we can think to is, as paper said, maybe we can train the language modeling for some iteration, and after those iterations, we start training the discriminator. So instead of loss backward, maybe we can change these functions somehow that we get the loss of the language modeling and backward through it for some iteration. And after it is stable, we can move some of the weights to the discriminators or maybe some initial layers. So it has 2 depths. Maybe the first depths can be filled by the weights of the generator, and the second depths can be trained during the next training phase. So these are changes that we can apply, but this code is working in the LucidRain library. There are some explanation that how it is working. There are some Jupyter notebooks. I hope that I could understand it well and I could explain it well. Another thing that is remained is, as I said, we have the name of discrimination layer, and we say hidden layer extractor from this model, extract hidden layers and add some linear layer to them. And by doing that, we are updating the discriminator. So we say discriminator is the hidden representation of the discriminator plus a linear layer with a discriminator dimension, which is 512 format. That's it. I hope you enjoyed the video. I appreciate if you leave the comments, share the video with your friends, and subscribe. Thank you and have a good day.